Howdy and welcome back to this lecture series on astronomy. This is lecture 4 for Astronomy 103, spring of 2022. Today we're going to be talking about essentially the dawn of astronomy and the events leading up to the Copernican revolution. In lecture 5 we will be talking about the revolution itself, how astronomy went from a geocentric universe to a heliocentric one, with the advent of the model created by Copernicus superseding the model created by Ptolemy. I can never get that right. So, the beginning of our story, as it were, is when the Greeks, at least the beginning of the story in the West, comes from the Greeks. And a gentleman by the name of Hipparchus was the first to accurately plot out the positions of the stars and what will later become the planets in the night sky. And he did so with fairly good accuracy. And this led to certain discoveries or certain behaviors of the planets that needed to be described and needed to be explained, which led to the formation of the first construct of the universe, or led to the first early models of the universe. Now, the 5 planets that we can see, or the 5 planets that they could see, were Mercury, Venus, Mars, Jupiter, and Saturn. These are the naked eye planets. These are the planets that are visible in a dark enough sky at the right times with your unaided eye. You don't need binoculars or telescopes in order to see them. Now, these were referred to as wandering stars by the Greeks, or planets, as it's translated. And they noticed a few fairly peculiar things about these wandering planets, or wandering stars, is that over a given night, all objects move from the rise in the east and set in the west. But the sun and the moon, they already knew, changed positions with respect to the background stars. You wouldn't find, say, for example, the moon to be in the same constellation over the course of several days or weeks. But they also noticed this in terms of actual stars themselves. There were these wandering stars that also shifted position and seemed to move in relation to that background field of stars, move from west to east. They were also tended to be brighter than most other stars, particularly Venus and Jupiter, and they also seemed to vary in brightness over time, which is unusual for stars, or at least the stars that they could observe. These wandering stars also seem to be travel along the same path, a path we refer to as the ecliptic. That is the orbital path of the Earth around the Sun. And all of the major bodies in the solar system move along the ecliptic. There are some minor adjustments or minor variations, but for the most part, they all move along this ecliptic. So from an earthbound observer, you could effectively draw a line through the sun, through the planets, through the moon, and they all travel along the arc going from east to west. But there was one particular motion of the planets that was very difficult to explain, and ultimately was what drove the need for some model to be created in order to fully understand what was going on with these particular wandering stars. When it came to, and the motivation for wanting to know where these planets came from had less really to do with agriculture, and more to do with simply astrology, the idea that the heavenly bodies could impact human life. And so there needed to be some sort of predictive model so that on a particular day or a particular night or a particular time, you can know where, say, Mars was in the night sky, whether or not it was in the constellation of Leo or Cancer or so forth, because those were auguries. Those were ways of foretelling the future and so forth. What they noticed, this thing we refer to as retrograde motion, is, as I said, for the most part, if you were to look at a planet over the course of several nights, you would notice that it moved through the constellations from west to east. But not always. Occasionally, the planet would seem to slow down in its motion, almost stop in its motion, and then reverse direction, and then slow down, stop, and then reverse direction again. So in this image, you can see see images that were taken of Venus, taken of Mars, every couple of weeks or so, and so you can see this loop-to-loop pattern as shown or displayed on a background field of stars. The other thing, hopefully, you can notice from this image is that not only is the motion strange, the motion seeming to start back up again and stop again and start back up again, but the planet seems to get brighter as it goes through this motion and then dimmer again. So not only do the ancient astronomers need to come up with a model which explains the motion, but also why the planet appears to get brighter as it goes through this motion. Prior to Aristotle, there were a number of notable astronomers, or natural philosophers, as it were, that led to innovations of our way of thinking, or were, well, innovations of our way of thinking. Let me point out two of them. First was, I don't remember which order they came in, but the first that comes to mind is Eratosthenes. Eratosthenes was the first to demonstrate that the Earth was in fact a sphere, and he did so using two sticks. By placing, or rather, a stick in a well, he noticed that in the city of Syene, on the summer solstice, the sun's light at noon went directly down the well. There was no shadowing within the water during at noon at summer solstice. It was directly overhead. And so what Eratosthenes did was, on that same day, he moved 50 stadia, or 500 stadia, that was the canonical unit of length at that point, similar to a mile, up to Alexandria, and he drove a stick into the ground, and he looked at the shadow cast by the sun. And what he correctly deduced was that in order for this geometry to work, in order for there to essentially be no shadow located at Syene during the summer solstice, and a shadow present in Alexandria on the same day at the same time, the Earth must be spherical. No other geometry would allow for that to occur, or allow for that to occur given the measurements that he had. And not only was he able to deduce the Earth was a sphere, but he accurately measured the radius of that sphere. And given the fact that he's using sticks, it is phenomenal that he got even close to an accurate value. And Eratosthenes' value of the radius of the Earth is about 10% of the actual value, which to me is astounding, particularly given the precision of the instruments that we have today. So the Greeks knew that the Earth was a sphere. But they didn't understand, but they were still somewhat unclear as to the shape and primacy of the other celestial bodies. A gentleman by the name of Aristarchus of Samos, I believe. It's definitely Aristarchus. There are a few of them. I think it was the one from Samos. He believed that, in fact, the sun was the center of the universe and the Earth revolved around it. And he believed that the sun was a large burning rock in space. And he also tried to measure the distance from the Earth to the sun using a technique involving the timing between full moons. Unfortunately, that technique is very inaccurate. It is not the best technique to use. And so the value that I got was, while it was far larger than any perceived distance between those two bodies previously, it was still drastically underestimating or undervaluing that distance. And unfortunately for Aristarchus, Aristotle's philosophy was taking hold, and Aristotle proved to be the better speaker and the more convincing rhetorician, I think that's the word. His arguments were um, much more believable, as it were, much more convincing. And so Aristarchus was driven from Athens. He was exiled for his beliefs that the sun was the center of the universe. So while he was, thankfully for him, he wasn't burned at the stake. He was a first example of how scientific views can cause someone to be persecuted. So what was Aristotle's philosophy? Aristotle, the student of Plato, who in turn was a student of Socrates, was a highly intelligent individual. He was perhaps the most renowned of the ancient natural philosophers because his views went beyond just simply the study of philosophy, but also were integral in the beginnings of physics, astronomy, and biology to a certain extent. But Aristotle was a deductive thinker. He had a large worldview of what the universe should be, and then he tailored his explanations for smaller phenomena to that larger worldview. Some of his worldview are that heavier objects would fall to the earth faster than lighter objects. That in order to keep something moving, you had to provide a constant impetus, constant force to keep that thing moving. So, for example, if you shoot an arrow, it's not momentum that carries the arrow. It's actually an impetus behind the arrow causing it to fly. But from an astronomical point of view, he had a few ideas that unfortunately stuck for an exceedingly long time, about two millennium, all the way up till the 1500s. And these were that the Earth was the primary body in the universe. It was the thing which all things revolved around, which I suppose made sense to him, because basically from his viewpoint, he basically sees the world from his feet, and so obviously where he's standing is the center of all things. He also believed that the Earth was not rotating. Because his rationale for that is birds don't fall out of the sky. If things are rotating, then obviously wind or some action is going to cause things that are flying to be blown out of the sky. What he didn't understand was the concept of reference frames and conservation of momentum. So he believed the Earth was prime, was the center of all things, was not rotating. So in order for the stars to move, the planets to move, and so forth, those had to be on spheres of their own, rotating around or over the Earth. Now, the reason why they had to be on spheres is because a sphere was the encapsulation, or the geometric encapsulation of perfection. An unblemished sphere was the idea of perfection. So was uniform motion. Aristotle was not incapable, but he refused to accept the idea that impetus could be variable, that a force moving something along would change in its intensity for reasons he couldn't understand. So because he could not understand those reasons, he believed that those things must be constant. So he believed in spheres. He believed things revolved or moved in spheres, or on circular paths, rather. And he believed in uniform motion. Those key things held for, like I said, a couple millennia. Put together, or pushed forward beyond the Hellenistic era to the church, because the church latched on to the idea of Aristotle's thought, because so much of Aristotle's worldview from his thoughts on physics and biology and so forth, they seemed to be correct. The observations that were done at the time seemed to be in line with what Aristotle was teaching. And the idea that the earth was the center of creation was very attractive to the early church. And so they latched on to Aristotle's beliefs to better legitimize what the Bible was teaching. And so that brought us forward. So what exactly is geocentrism? Basically, the geocentrism is the idea that the Earth is the center of the sun, or excuse me, the center of the universe and all things going around it. Now, as I said, this was not a natural-born idea. There were some out there, some astronomers, or some Greeks out there, who entertained at least the idea that the sun, the brilliant luminary in the sky, that may actually be the center of the universe. But they correctly deduced that if that were the case, if the Earth were moving with respect to the sun, that we should see what is known as stellar parallax. We should see closer stars moving relative to a background field of stars. And I'll explain that more in a moment, but essentially based on the angle at which you view a closer object in relation to further objects or objects further away, that object will change in its perspective. They didn't see that. And so that was their hypothesis. The hypothesis was if the Earth is moving around the sun, then we should see stars moving relative to each other, backwards and forwards. They didn't see that. They made observations and could not see this effect. So they were left with two options. Either A, reject the hypothesis entirely and move to the Earth was the center of the universe, or they could admit that or believe that the stellar parallax was exceedingly small and too small to be observable. Now they, excuse me, they went with the former. They basically, because they could not see the stellar parallax, they concluded that the heliocentric idea or the heliocentric hypothesis was in fact falsified. In reality, it's the latter. Stellar parallax is an exceedingly small effect. You actually need a moderate to large size telescope in order to view this effect with any sort of accuracy or precision. Excuse me. So it was many, many years later, many centuries and millennia actually later, that stellar parallax was proven to be an actual effect. So what is parallax? Parallax, as I said, is the shift or apparent shift of a star in relation to the background stars. So let's take the example of a fictional star that is closer to the Earth relative to the Big Dipper. Now, from one point in the Earth's orbit, we can see from the diagram that the star appears to be within the bowl of the Big Dipper. Around 6 months later, when you view that same star, it's going to appear outside the Big Dipper over to the left. Now, as I said, our stellar parallax is far too small to see, so you would not see this effect with this sort of size in reality. But this is basically this is a not to scale example of what parallax would look like. So on one side of the sun, or one part of the Earth's orbit, the star will appear, say, to the right. As the Earth orbits around, the star will shift over to the left, and as it completes its orbit all the way around, it'll shift back over to the right again. Man, excuse me, I don't know what's got a frog in my throat. Maybe I should edit those out. Anyway, if you want to basically see this effect for yourself, well, you've probably already seen this effect. If you're traveling in a car, traveling down, say, the interstate, you will just naturally notice that the guardrail or the road signs are whizzing by you very quickly. But if you look into the middle distance, say, residential houses or residential areas or what have you, they are moving by you, but much slower. They are not whizzing by you like the signs are. And then if you look further in the distance, either forests or mountains or what have you, those appear to be not moving at all or moving very, very slowly. So that is a, I would say quintessential, maybe that's the wrong word, that is an excellent example of parallax, and particularly the quantity that we are interested in using parallax, because parallax not only doesn't only prove the heliocentric model, but it's a useful tool for astronomers. But if you want to demonstrate parallax without moving, you just hold up your thumb, close your right eye, and then line up your thumb with a distant object. And then close that eye and open up your right eye, and then go back and forth. Camera 1, camera 2, camera 1, camera 2. Hopefully what you should notice is that your thumb appears to shift left and right with respect to that background object. The reason for it is if you hold your thumb up and you say to draw a line from your eye to the thumb, it would go off in, say, that direction. If you do the same thing with your left eye, it's going to hit your thumb and move off into that direction. So the two eyes have a small make for basically a small angle in relation to your thumb. So that is useful for well, it's useful for a number of reasons. But when we talk about eyesight, something you're probably familiar with is something called depth perception. The idea that we naturally can just sense or detect that things are close and far away. The reason why you can do that is because you have two eyes that are spaced apart from each other. The further apart they are, the keener our sense of depth perception would be. Which is unfortunate for someone who loses an eye. When they lose an eye, you lose a great deal of your depth perception. One of the ways that we have this depth perception is that your brain is actually calculating parallax using the information from your two eyes all the time. And so it notices by looking at particular objects, you can use this sort of parallactic effect to determine what things are close and what things are further away. Now, so what does parallax actually give us? Like I said, outside of proving the heliocentric model. Well, it gives us distance, as I said, depth perception. It allows us to determine the distance of distant but close by objects. So the distances to stars that are closer to us than, say, background stars, or distances to planets, or really any astronomical body, anything that is far away. Now, when you're talking about determining the size of I've already referred to it, the size of the movements of objects along the sky, we're dealing with angles. And whenever you deal with angles, you're inevitably going to have to deal with trigonometric functions, sine, cosine, tangent, and so forth. And on top of that, if you are dealing with angles of objects that can be represented as being on a sphere, you have to deal with the lovely and imaginatively named spherical trigonometry, which is a whole level more complicated math. But thankfully, at least in terms of parallax, we can use what is known as a small angle approximation, or small angle formula. What that means is, for example, sine theta, if you take the value of sine theta for very small angles, your answer is theta. Basically, you get the angle out of it. And so the sines and the cosines and the tangents all literally fall out of the equation. And the equation that we're going to use for distance is displayed on the screen, where A is the parallactic angle in arc seconds, and that's equal to 206,265 times d, the size of the object, over d, the distance the object is away from us. In this case, we're actually flipping it. So in reality, d is actually the size of the orbit of the planet of the Earth going around the sun, and then you can basically flip that around, and you measure A, and then you can calculate D. Ultimately, what I would like you to get from this, the takeaway point from this, is that the parallactic angle and the distance to the object are inversely related to each other. The smaller the parallactic angle, the farther the object is away from the observer. The larger the parallactic angle, the closer it is to us. So why were the Greeks not able to observe this? Very simply, the parallactic angles are tiny. For the closest star, Alpha Centauri, we're talking about parallactic angle in fractions of arc seconds. Excuse me, in arc seconds, fractions of arc minutes. An arc second is unbelievably small. One arc second, the angle of one arc second is the angle over a dime if that dime were 21 kilometers away. There's no possible way that a human eye can view that. And that's the closest star. That's the largest parallactic angle that we can actually measure. So, as I said, the parallactic angle is inversely related to the distance to the star. And we can, by measuring the parallactic angle, we can then determine, as I said, the distance. This is what we refer to as the second rung of the cosmic distance ladder. The first rung is radar finding. We emit a radar signal, we put out a radar pulse directed towards an object, say Venus, for example. It smacks into Venus and it comes back. And we time the amount of time, or we measure the amount of time it takes from the emitted pulse to the received pulse. And since the pulse is traveling at a finite speed, that time difference gives us a distance. Let me get this right. Distance is equal to velocity times time. So you know what the velocity is, you know the time, you can get the distance that way. Very simple calculation. And there are a couple of nuances to it, but that's essentially it. So that's our first rung of the distance ladder. We can use that to essentially determine the distances of things within our inner solar system, or within our own inner solar system. But then we can also test the viability of parallax. We can see whether or not parallax can be used to determine distances that are even further away. We can measure, so for example, we can use radar finding to measure the distance to Venus. We can use trigonometric parallax to also measure that distance to Venus, because it will move relative to the Earth's motion, or due to the Earth's motion. And if those two values are the same, because those two techniques are independent of one another, they basically utilize different geometries, different physics, then you're confident in the idea that trigonometric parallax, which can essentially see farther or measure farther, is a viable option. Hence why it's a ladder. One measurement or one technique is used to calibrate or verify the viability of the next rung up. And this is a crucial thing that astronomers do, is one technique will often be limited by some physical factor, be it distance or luminosity of this, or brightness of an object, or what have you. But another technique can see farther, measure dimmer. But we cannot trust that technique unless it's been verified by the tried and true method of the technique for smaller or brighter objects. When it comes to parallax, I'm going to put out a supplementary video. I highly encourage you to watch it, but it's not strictly necessary. It is called The Rob Explains Parallax. I will explore parallax in a little bit more detail, or with a little bit more nuance, and actually use a computer simulation to demonstrate what the movement of these stars and how the distance gets affected, affects the parallactic angle, but also the orbit size affects the parallactic angle. So it will answer the question, what would happen if we put a telescope on Mars? Would that help would that increase our range, essentially? Would that allow us to measure parallactic angles more accurately? In brief, the question then becomes, how far can we use this technique? Now, because of the Europeans, we are blessed with the Gaia satellite, and because we can use because of the precision of the Gaia satellite, we are able to measure the parallaxes of billions of stars within the galaxy. So we can essentially determine the distances of every star in this galaxy so long as Gaia can actually observe it. So its range is approximately 50,000 light years or maybe slightly greater. However, it is not great enough to get us to the next galaxy over. It's not great enough for us to determine the distance to the Andromeda galaxy, or certainly not the Triangulum galaxy, and the M81 is right out. We actually have to use the next rung up, which is called utilizes variable stars. But let's not get ahead of ourselves. Let's move on to the first models that I intimated at the beginning of this lecture. What was the first model that astronomers created to explain the motions of, specifically the motions of retrograde planets, or retrograde motion? Well, for all of Aristotle's brilliance, he was not a mathematician. And so this task fell upon a gentleman by the name of Ptolemy, another Greek who lived in Egypt. And Ptolemy was the one who threw math at the problem. And the reason for this is you can have a wonderful sort of model or idea of what the universe is, but as I hopefully emphasized in a previous lecture, unless you can make a prediction using that idea, it's really not science. It's not really useful, and it is not a proper way of describing the universe. So Ptolemy looked at this and looked at Aristotle's ideas and tried to come up with an actual mathematical model that would be able to do these predictions, that would be able to say, all right, in 6 months from now, we will be able to see Mars in the constellation of Aries. Because that's really what they were ultimately after, is some sort of tool that allowed them to literally predict the future, or at least predict the future of where the planets would be in the night sky at various times in the world, or in the future. But Ptolemy had to fudge things a little bit, fudge Aristotle's worldview a little bit in order to make this work. Aristotle's worldview was simply that the Earth was at the center and the planets moved around crystalline spheres in uniform motion. Ptolemy couldn't get that to work. Mathematically, when he created that model and then tried to match future predictions with future observations, they were too far off. They didn't match up, and so therefore that hypothesis had to be rejected. So that left him with just, again, two options. Either reject the theory entirely or change it, or basically revisit it in some way, alter it in some way. And he chose the latter rather than the former. So what he did was, the Earth is no longer the center of the universe. It's just slightly offset from the center of the universe. We have this thing called an equant, which if you measure the distance from the center of the universe to the Earth, and then you measure the distance, take that distance to the opposite side, that position is called an equant. Now, again, Aristotle said that the planets moved around in crystalline spheres. Well, that didn't work either. So what he had to do was he replaced the crystalline sphere with a large orbit referred to as a deferent. So the planet will, to first order, move along that deferent, but its motion will be, there's an additional motion added to it. And so he takes something that we refer to as an epicycle. Think of it as a smaller orbit. And the center of that orbit is now positioned on the deferent, so that the center of that orbit travels along the deferent. The planet is now placed on the epicycle. And so the planet orbits around the center of the epicycle, which in turn orbits around the deferent, which is defined to be around the center of the universe. And so how does this explain retrograde motion? Because again, it has to explain that the planet appears to slow down, reverse direction, speed back up again. And also the planet gets brighter when it does so. Well, in this case, the planet is literally doing that. The planet, from the Earth's perspective, is slowing down when it moves around in its epicycle, and it's getting closer to us, hence why it appears brighter. And so it literally does loop-de-loops around the universe. The problem becomes that when he first introduced this model, everything was great. When he first introduced this model, the precision of the observations that were made were poor enough that the inaccuracies of Ptolemy's model were hidden. So if, for example, if people couldn't observe the position of something within, say, 5 arc minutes, then Ptolemy's model could be off by 5 arc minutes either way, and the prediction would still hold true. But that became a problem as we got better and better at observing the stars. First, we used no instruments. We simply used the naked eye. Or, I should say, I backed off that. Hipparchus actually used rings on sticks. So, very, very crude instruments. And then we moved to more sophisticated instruments like astrolabes and meridian transit instruments. And our observations became more precise, and Ptolemy's model predictions proved to be wrong. Not by a lot, but at least not in short time distances, say on the order of months. They weren't that off, but if you were to try to calculate where the position of a planet was a few years from now, it would be incredibly off. So again, rather than reject the model entirely, they just, the astronomers of the day just said, all right, we'll just add to Ptolemy's model. We'll just make it more, we'll just add more epicycles. And that seemed to do the trick. That seemed to reduce the errors or reduce the discrepancies between the predictions and the observations. So again, all was great until we get to Tycho Brahe. Tycho was a Danish astronomer who is, depending on my mood, or I should say Tycho, I have been corrected. Tycho Brahe, depending on my mood, is my favoriteest astronomer, hands down. Except Galileo. Galileo, Tycho, they're kind of up there in the same way. I could go off for hours about Tycho. Well, maybe a couple hours about Tycho. But highlights, the dude lost his nose in a sword fight over a math proof with his cousin. He also had a pet moose who he liked to get drunk. And unfortunately, he didn't have the moose long because while a drunken moose can go upstairs really well, a drunken moose cannot go downstairs very well. So sadly, the moose came tumbling down. And third, he died ignominiously. He essentially, because of court customs, he could not leave the dining room table, prior to his superior ranked guest. And apparently it was a very long dinner, and he should have gone to the restroom beforehand. We don't know exactly whether or not his bladder burst or whether or not he later died of a urinary infection. But yes, because the man could not take a piss, he died from it. So yeah, he was a very colorful individual. You got another example of his character. The painting that you see here was painted on the inside of the large dome in Uraniborg, his crowning observatory. Now, why do I mention Tycho? It's because he was the best visual observer we have ever had, or at least definitely of that era. All of it, he devoted himself to determining the positions of stars and planets with the dreams of creating his own cosmology. He realized that the Ptolemaic model had flaws. And so he believed that if he could make precision observations better than anyone else had ever done, he could use those to essentially create his own cosmology away from the Ptolemaic model, or greatly reinvent the Ptolemaic model after his own image, as it were, and gain notoriety from there. And unfortunately, he was not able to do that because of his untimely death. And we'll get into the ramifications of that death and his observations later on. But Tycho was able to measure things to an accuracy of 1 arc minute. To give you a sense of scale, as I may have mentioned in a previous lecture, the full moon is 30 arc minutes in size. So he was able to determine the absolute position of a star to within 1/30th of a full moon, which is astounding. And that leads us to why the Ptolemaic model ultimately failed. Is because even with the complex Ptolemaic model that he had at the time, he could not explain, the Ptolemaic model could not explain an 8 arc minute discrepancy in the predictions related to Mars. And that was something that Kepler noticed and banged his head against the wall trying to rectify for nearly a decade. Now the slides I skipped over, the first slide is explaining retrograde motion in a heliocentric way. And just briefly, what this the real way, or in reality, how retrograde motion is explained, is that the Earth simply overtakes Mars in its orbit. Kepler will tell us that planets that are interior to other planets are moving faster. So the Earth will lap Mars repeatedly over time. And the retrograde motion is simply a line of effect line of effect phenomenon. Very much like the parallax is, in that if you are on one side of Mars, you're going to see the planet with respect to a different field of stars, and if you're going faster on the other side, or if you're trailing Mars, you're going to see it on a different background field of stars than if you're leading Mars. Now, I will also have a supplemental video. Again, it is not required, but highly suggested that you watch it. I will be using this particular applet to talk about the differences between the geocentric model and the heliocentric model, and particularly in how they explain retrograde motion, and ultimately why one does not quite fit the bill in its explanation for the other. I think you can guess which one fails. All right, with that, I will bid you adieu, and next time we will finish with talking about the actual Copernican revolution, started by Nicholas Copernicus, who had the academic audacity to say, enough is enough. This model simply does not work. Let us at least try another way of thinking. Let's at least see what happens if we put the sun at the center of the universe. All right. Have a good night.